So let's start off with this example right here. So we have a simple linear machine learning problem. So we formalize it here. We have our loss function. We have our training samples, so n training samples. And our goal is to learn a shared mapping W across all training samples. However, okay, these training samples right here are not allowed to directly interact, okay? So this is a drawback, which means I'm learning this mapping, but I'm not considering the similarity or the relationship between these points. So maybe this point is very similar to this one, so I should kind of, take that into consideration when learning my mapping function, my shared mapping W. So this kind of approach looks at each data point individually. All right. So we have what we call an individualistic approach. So these are individualistic points. The data samples, they live independently on a high dimensional manifold. All right. So so here, even in manifold learning, for example, so this is the high dimensional manifold. You have different data points, and you want to do regression problems. So you want to identify a path here that regresses these points, right? So now this path is projected here into a two-dimensional plane, right? And all of these points with a manifold, there is a projection there. We can see this beautiful projection, but still, even in this manifold learning that we're doing right here, and we were able to, let's say, learn and discover very well the embedding manifold of the data, okay, or the manifold where the data is nested and lives, they're still independent, okay? So in manifold learning, we learn also how to calculate the similarity between points. So remember here, we want, these two to be close. So the similarity here needs to be somehow preserved, right? So I didn't talk about this in detail, but here the manifold learning is based also on kind of, preserving the neighborhood. So that's the idea. So it preserves the neighborhood. It tries to keep similar points in the original space, similar in the target space, but not how to, it doesn't connect the points, okay? So here with manifold learning, we have kind of taken one step forward, which means we're not trying to use the original space. We're trying to discover a space where that represents the structure and the geometry and the distribution of the data very well. But however, this space is still individualistic. It means like it looks at each point kind of independently of all other points. There is no actual interaction. We're not using, multiple interactions to kind of model or represent this manifold. Now, we're actually one step away from that. So let's look next. So here, this is, the data, the input data that we have. Let's say that the data structure on the manifold or distribution looks like this. And then all we need to do is actually to be able to model the interactions and include the interactions between these points during our learning is to learn what we call the adjacency matrix, or to define the adjacency matrix of all these points. So here we have all our training points. Okay, so if we have n points, we will have n by n matrix. And in this matrix, this will be the matrix that represents or encodes the interaction between all points. So for example, here we may have a graph that looks like this. All right, so something like that. And these will be connected in this way, which means we'll have a sparse graph because in this example, these two nodes, let's take a different color. So these two nodes are actually not connected directly, okay? So their connection is 0, right? So these also two nodes are not directly connected. So you can see that in this graph, so here we build a graph, and this graph allows us to model the interaction between different points. And when we are learning how to embed, a single point right here, okay? So let's take a single point. So if we learn how to embed this point or represent this point xi into a new dimensional space, I'm going to take into account its interaction with its neighbors. So now we're learning the embedding of this guy, not with respect to only one single sample in terms of similarity, but by looking at its, kind of neighborhood. All right. And this is very important because here we're trying to learn a structured manifold, a manifold that is encoded in a graph. And this manifold will allow us to better represent the data because now we're not looking at these guys independently. Okay, we're not training the model independently. Actually, these guys are interconnected. Many of them happen to be very similar to one another. So many of them happen to be, close to one another. So we're somehow building a huge graph that connects all these points. And, if the points are very close, so they will be within the same kind of graph core or module. And if they're far away, they will have kind of this these long distances between them, okay, or long edges. So the idea here is that not to learn independently, but to co-learn. And this has a very interesting aspect because if I look at this point without considering all of these somehow, it's very reductionist. But if I look at this point and I consider its relationship with all other guys, whether it's connected or disconnected, then I am taking into account the similarity in the distribution of the training points in that particular training set or cohort or batch, and I will be able to kind of learn better. Okay, so this is, basically it uses a graph to model and capture the relationships between pairs of data points, and each sample interacts with all other points. So this is the second learning paradigm. So the first learning paradigm uses individualistic points, and the second learning paradigm where we actually define a graph that encodes the relationship or represents or models the interaction weights and strength between different data samples. Now we move to the collectivist learning paradigm where we have collectivist points, and data points actually they co-interact, they co-learn together via this graph structure matrix A. Okay, so of course here, so this is our graph. We have the features. We define our adjacency matrix here. We have, a few nodes that are similar, so they are connected. And we can look at the topology of the graph, its structure, the connections between these different nodes. When we want to learn the embedding or predict the label of this node, we should not predict the label of this node independently. We should predict the label of this node dependently from its neighboring similar nodes. Okay, so that's the basic idea. And of course, here we can add edge features. And we can, in addition to, we can add node features. So we have the features here for nodes. We can add edge features. And remember, we've got a graph to learn on now. Okay, cool. So now that we moved from all of this, machine learning to manifold learning, and then from manifold learning to graph-based, learning, these concepts now that we have a graph, so then we can do, for example, classification using this graph. So we encode the data, we represent the data as a graph, and then we will learn today about a simple graph neural network, which is GCN. So we'll see this later. So we can apply a graph neural network here that allows us to kind of learn the embeddings of each node. So we learn how to encode each node on the graph. Okay, so now it's not just on a manifold or a new space, but on this graph. And this graph embedding of each of its nodes will allow us to kind of, integrate this knowledge and classify, for example, the graphs. So how do we actually get the node features? Okay, how to get the edge or graph features? So this is a big question here. So you may think, okay, so now we have modeled the data as a graph. We need to kind of define, extract features from the graphs, because if you think about this as a sample, right? So this is, for example, let's say I have a sample like this. So this is my graph. It looks like this, all right? and I have the connectivity matrix A. So how to extract features from this graph? So I need to classify this graph. I need to know if this graph is, for example, this molecule. If it's a molecule, I want to know if this molecule is, you know, poisonous or is it harmless, right? So basically, to know that, we need to kind of extract features. So the next step here is how to extract features, feature extraction from A, from the graph, from only A. So for now, we have only A, the structure of the graph encoded in the adjacency matrix. All right, so we're going to take a very simple example here. And yeah, so there are, in graph theory, there are so many methods that allow us to, you know, like extract features for nodes, edges, graphs, okay? And the simplest way, so I'm going to cover these, but if you guys are interested to learn more about, you know, these approaches, you can read on that, and I'll provide a few resources in the video caption below. And you can also have a look at the graph theory playlist. So I cover many of these fundamental classical feature extraction methods. So there are 3 types here, and I'm going to give you just a few simple examples. So node-based features, edge-based features, and graph-based features. So let's start with, for example, the node-based features. So here, node-based features, as you guys, if you guys remember, in the first lecture, we talked about centrality measures and topological roles and topological kind of values, right? So measures that we can use to characterize the importance of a node. For example, here, we can extract, you know, node-based features. So this graph G, so this is graph, for example, G. So what we need to do, we kind of need to calculate or extract for each node, if we're going to do node-based classification, right? So we need to extract features for each node. So for example, for node, let's call it xi, so this, or node I, so for simplicity. So for node I want to extract a set of features, let's call this xi, belonging to RD. So I want to extract D features. So for example, I can use what we call centrality measures or topological measures. For example, we have seen before degree centrality, okay? So you can use between a centrality. These are measures that allow us to quantify the importance of a node in a graph. So if the node is a hub node, is it a peripheral node? Is it a node that, you know, like connects different parts of the graph? So it's very important. So we can use these topological measures, and by doing so, for example, here, if we use the degree, so the degree of this node is 3, so we can put 3 here. And you guys can see that manually we can extract these features only from the topology of the graph. Okay, so each node I will be represented by this vector, and then we can learn on these nodes. So this node here, for example, could be let's say, if we want to predict, you know, trees, and you have, I don't know, birds, right? So maybe these will be birds, and this will be a tree because they're close to. And here something is off. This, maybe we should change that a little bit. So anyways, far away, you can see this, actually it's connected, it's far away. But the idea here is we want to get the label, and the label here will depend on this feature. So we can train, for example, an SVM classifier on these features that we extracted from our graph for each node, okay? So, right, so now the edge-based features, the simplest way is, let's say, so we have a graph. So this is our graph here, and we have our adjacency matrix. So this is an undirected binary graph. And if it's also a weighted graph, what we can do, we can simply vectorize the upper triangular part of diagonal, because the diagonal is self-connection, so we may not need that here. So we take the upper triangular part, okay? And then we vectorize it. And if you have n by n matrix, the upper triangular part will be n times n minus 1 divided by 2. So this is the size of the feature vector x that we have extracted right here. And this is edge-based. So here we have actually vectorized the whole graph. So the weight of each, edge may be discriminative. So we can use this weight to do some classification, but it's not very important here. So let me actually move this right here. So it's better to kind of move it right here, because there are different ways of doing this, but I will explain. So here, if we concatenate, this is a way of vectorizing the matrix, but what we want actually to distinguish or to extract features for different edges, okay? So one way is if you want to represent the whole graph, you can stack them all. So here we actually extracted edge-based features, and by stacking them, okay, all these weights, we get a feature vector that represents the graph, okay? So this represents the whole graph, and this is the graph is equal to VE, and it has the matrix A, all right? So this feature vector represents the whole graph. Now, if you want edge-based, having a single, value is not important. So let me take this back. So here, a single value means one value right here. So this is the weight that connects nodes I and J, okay, I and J, and it could be, for example, 0.5. So if you're going to rely only on this, you have only one feature. So we want to extract multiple features for the single edge. So a single edge, let's call it EIJ, will be represented by many features, by a set of features. So this set of features, we can first call this set, so EIJ will be represented by a vector X, and in this vector X, we can have the weight, so we can put the weight, okay, WIJ, and we need to identify or define different features. So one feature here is also centrality measures. So you can have, for example, between a centrality for edges, for the edge connectivity. So basically this tells us if this edge is so important, it lies between all paths that connect, all pairs of nodes between in the graph. So if you take any pair of node, it means that you need to traverse to walk through this edge, okay, to get from A to B, to get from, for example, from this node, let me choose different. So from this node A to node B, or let's say B is here, you always need to kind of, most of the time you need to traverse this path. So this path has a high betweenness. If it has high betweenness, it means it lies between all pairs of nodes and walks that connect them. So this is also topology. So you can do or extract a lot of topological or topology driven measures that allow you to put values here, quantify or measure the importance of each edge in the graph, okay? So this is for a single edge, and now once we have this vector, we can apply a linear, for example, a regression model, because this will belong to RD. This is our sample here, and for each edge, we're gonna have our training sample. If we have some also target scores or target values, we can learn a mapping through W, as we have seen earlier, to be able to predict this. So basically, these are basic techniques, and you have also walks. You have walks on graphs, number of walks on graphs. So you can calculate the number of walks, the average walk on a single edge, and have a number there, and you put it here in this vector, okay? Now, for the graph-based features, so for the graph-based features, we can either, extract the features of the whole graph from edge features or from node features, and we can combine both. Like, for example, here we combine different edge weights. So this is if we take this as one feature representing one edge, then if you stack them all together, you're going to get that. What we can also do is to, concatenate or to add up, combine. So this is, one way, combine node features, okay? So you combine node features into a vector that represents the graph. So if you have the centrality measure of all these guys, so you have centrality measures of these kind of nodes, you can just stack them all together, and this will represent your graph G, okay? So that's another way if you're classifying graphs, or you're like learning from graphs. So, however, so all of these are traditional methods. They extract features using the A matrix, okay? So all of these methods, these conventional methods, they cannot use node, edge, or graph features. So which means they don't use the A, the feature matrix X, and the E matrix here. So they are only relying on the adjacency matrix, which is the topology, the structure of the graph, okay? So all of these methods cannot integrate that. So these are basic graph theory analysis methods. And these approaches cannot obtain embeddings for nodes, not in the training set, okay? So so here we cannot get embeddings. We cannot learn how to represent a node in a lower dimensional space. So if we add, for example, a node, we need to recalculate. So there's a typo here. So we need to kind of recalculate all node feature representation. So we need to recalculate, okay? So if we recalculate all node feature representations, that wouldn't be efficient, okay? So what that means, if we have a graph like this, and we classify the nodes in the graph, and I have a new node. All right, so for example, I add a new node here, and I want to know the label. So if you guys know this, now that we have changed the topology of the graph, so this is, we need to update the A, we need to learn the centrality, because now this node has two neighbors, not only one, right? So every time you add a node, all these features will change, that the static features that we extracted, which is not good. It means that, you know, you need to recalculate and update all these features again. And these approaches do not allow you to easily extract these features again for an unknown node. So doing this for unknown nodes may not work. So that's, you know, kind of the these are the main the main disadvantages of using classical graph theory to extract features and represent parts of graphs or the whole graphs, the entire graphs. So so that's the story. So I think we can actually stop here, and the question that may come to your mind, all right, now that we're having, you know, all of these, that we represented our data in a collectivist way, we have a graph that allows us to co-learn and benefit from other nodes, right? Not just solving the task just for myself, being individualistic here. So we're trying to kind of build a community of nodes, and we co-learn together. However, if we're going to use classical methods, these classical methods, they do not embed or allow us to have annotated graphs, which means graphs with nodes that have original extra features, edges that have extra features. Also, when we add a new node, we need to recalculate all these classical node, edge, or graph-based feature measures or extraction values, right? Extracted values for all these nodes. So that's not good. Now, this is where GCN comes into play and comes as a solution for this. So we will see this in the second section.